This section examines fuel pumps for electronic fuel injection systems. In an electronic fuel-injected engine, the fuel for the injectors must be pressurized before the engine can be started, so an electric fuel pump is necessary. This is an electric rotary pump. It can be located in the tank or externally on the underside of the body. Petrol enters at one end and leaves at the other, so it's always full. This lubricates the pump motor and keeps it cool. The pumping element is a roller cell device driven by an electric motor. A rotor disc is mounted eccentrically in the pump housing. It has recesses around its edge containing metal rollers. As the disc rotates, centrifugal force pushes them outward. This forms a rotating seal, and fuel is carried round in the cavities formed between the rollers. Because of the eccentric mounting of the disc, these cavities expand as they pass the inlet and contract passing the outlet. This pressurizes the fuel and forces it into the fuel line. The pump can also be an impeller type, which is less noisy. For a short time after an engine is switched off, engine temperature keeps rising, and that can cause excess vapor in the fuel lines. This pump stops this with a non-return valve on its outlet, which maintains the pressure in the fuel line during that short time. If a fuel blockage occurs further along the fuel line, it can overload the pump motor and make it overheat. So a high-pressure relief valve inside the pump lets fuel keep circulating. When the pump is mounted externally, a low-pressure pump can be used to supply fuel to the main pump's inlet. This low-pressure pump is mounted in the fuel tank. It's a centrifugal type and electrical, and it operates in the same way as the other high-pressure pump. This section examines fuel filters for electronic fuel-injected petrol engines. It's very important to supply clean fuel to the fuel rail in EFI systems. Small particles of dirt can block an injection nozzle and cause an irregular spray pattern. Any water in the fuel will corrode the inside of the injector, especially if the engine stands unused for long periods. The first filtering occurs with a strainer or fine gauze in the fuel tank. The next filtering occurs at the inline filter on the high-pressure side of the pump. This is a large capacity filter encased in a steel shell or an aluminium housing. This housing must be rigid to withstand the high pressures in the system. The filter is a pleated paper type with pore size of about 10 microns. A fluted support plate keeps the filter stable in the housing. The filter is directional and it must be fitted in the direction of fuel flow. Final filtering occurs with a small conical filter at the fuel entry to the injector. This section examines the fuel rail. The fuel rail is a large section pipe with an inlet connection from the fuel filter. The injectors are attached to the fuel rail, so they are each subject to the same injection pressure. Then, when they're open, they each inject an equal amount of fuel. This section examines the fuel pressure regulator. In multi-point injection systems, it's located on the outlet from the fuel rail. Fuel circulates continuously, but the fuel pressure regulator controls the quantity of fuel returning to the tank. This in turn controls the pressure in the fuel rail. It consists of a metal housing with a spring-loaded diaphragm between the two halves of a steel-pressed shell. A valve attached to the diaphragm controls the exposure of the opening to the return line. With the pump operating, fuel pressure builds up on the underside of the diaphragm and raises it against the force of the spring. The central valve is carried with it, which lets fuel return to the tank. Fuel in the rail is now kept under pressure that's determined by the force in the spring. As well, further control is needed as fuel pressure has to stay at a constant value above manifold pressure. Otherwise, the fuel quantity delivered won't be accurate. The spring housing above the diaphragm is sealed and connected to the intake manifold. Low pressure in the manifold then acts on the diaphragm and helps its movement against the spring. As a result, fuel pressure is continually corrected in step with changes in manifold pressure. When manifold pressure is low, as at idle, fuel pressure will be lowered. When manifold pressure is high, as at full throttle, fuel pressure rises. As a result, the quantity of fuel injected into the engine is set solely by the duration of the electrical pulse from the control unit. This section examines sensors for air measurement. The amount of fuel needed for each engine cycle varies depending on pressure changes in the manifold. That means manifold pressure needs to be measured. One way to do this is to measure airflow. Measuring airflow allows for changes in an engine that can affect volumetric efficiency, such as wear, combustion chamber deposits, and valve clearance. The vane-type airflow sensor is located between the air filter and the intake manifold. All the air drawn in by the engine is measured by this sensor. It's the main measurable variable for fuel control and metering. The sensor measures the force from the airstream on an airflow sensor flap. It overcomes the opposing force of a coil spring on the flap and deflects it. As the airflow increases, so does the deflection of the flap and its angle. A potentiometer converts the angular position of this flap into a corresponding voltage. This voltage becomes a signal and it is transmitted to a control unit. The sensor operates in a wide range of conditions. At light throttle openings, only a small amount of air passes, but the sensor must be able to measure it. The engine's intake strokes can cause the sensor to oscillate. This is counteracted by a compensation flap. It operates in a dampening chamber and moves in unison with the air sensor flap. Since intake manifold pulsations have the same effect on both flaps, the forces cancel each other out and measurement isn't affected. An adjustable bypass diverts a small quantity of air past the sensor flap. It is used to adjust the air-fuel mixture at idle speeds. The mass-type airflow sensor detects the mass of air flowing into the intake manifold. By measuring the mass of the air, it prevents changes in air density affecting the air-fuel mixture. The airflow meter has an electrically heated wire mounted in the airstream. A control circuit is linked to the wire and current is supplied to the wire to keep its temperature constant. The higher the airflow, the more the temperature of the wire falls, and the higher the current needed in the wire to keep its temperature constant. So how this current varies is a measure of what is happening to the airflow. Current flow variation is then read as an output voltage and converted by the ECU to an intake air signal. This determines the basic fuel quantity needed for injector pulse duration. The airflow meter can have a self-cleaning function that burns dust and other contaminants from the hot wire. This is done by the control unit heating the wire to 1000 degrees Celsius for approximately 1 second. This happens 5 to 10 seconds after the ignition is switched off. This function operates only when certain conditions have been met. For this vehicle, the engine must have reached operating temperature, and the vehicle must have been traveling above 10 kilometers an hour. In some types of sensors, the hot wire is mounted in a sub-passage connected to the main passage. This allows maximum airflow through the main passage. The hot wire may be sealed in a glass envelope. This protects the wire and eliminates the need for burn-off. In others, the heating element is a ceramic plate. Changes in engine speed and load cause changes in intake manifold pressure. This sensor measures these pressure changes and converts them into an electrical signal. It's called a manifold absolute pressure, or MAP sensor. The signal may be an output voltage or a frequency. By monitoring output voltages, the control unit senses manifold pressure and uses this information to provide the basic fuel requirement. It can use a piezoelectric crystal. If there is a change in the pressure exerted on this crystal, it changes its resistance. This alters its output signal. The sensor is connected to the intake manifold by a small diameter flexible tube. The control unit sends a 5-volt reference signal to the sensor. As manifold pressure changes, so does the electrical resistance of the sensor, and this in turn produces change in the output voltage. During idling, manifold pressure is low, which produces a comparatively low MAP output. With wide open throttle, manifold pressure is closer to atmospheric, so output is higher. The air vortex sensor uses whirlpools of air, or vortices, to measure the volume of air entering the engine. A triangular vortex generating rod disturbs the airflow and causes whirlpools of air to form in the body of the sensor. The vortices alternate from clockwise to anti-clockwise rotation, and they are staggered as they pass through a transmitter-receiver area. When there is no airflow, this transmitter emits a constant signal of ultrasonic waves to the receiver. When the engine is running, the vortices distort the ultrasonic waves. This modulates the ultrasonic waves reaching the receiver. This modulated wave is converted to an electrical pulse signal, which is directly proportional to the airflow. This is then used by the ECU to determine the basic fuel requirement. An air regulator or rectifier is located at the entry to the sensor. It reduces turbulence in the airflow passing the vortex generator. To maintain the air-fuel ratio within an optimum range, the control unit must take account of coolant temperature and air temperature. Extra fuel is needed when the engine is cold and when the air is colder and therefore denser. The coolant temperature sensor is immersed in coolant in the cylinder head. It consists of a hollow threaded pin which has a resistor sealed inside it. This resistor is made of a semiconductor material whose electrical resistance falls as temperature rises. The signal from the coolant temperature sensor is used to control the mixture enrichment when the engine is cold and is processed in the control unit. Enrichment occurs during engine cranking, then slowly reduces as the engine warms up. This ensures a steady engine response immediately after releasing the starter. The control unit continually monitors coolant temperature during engine operation. If the air temperature sensor is installed in the airflow sensor, it's positioned in the airstream, and it's called an intake air temperature sensor, or IAT. When it's installed in the intake manifold, it's located in one of the intake runners, and it's called a manifold air temperature sensor, or MAT. In both cases, it relays information on temperature and therefore the density of the air. The control unit can then vary the setting accordingly. This section examines the throttle position sensor. This sensor gathers information on throttle positions to allow the control unit to make adjustments according to operating conditions. It is located on the throttle body and operated by rotation of the throttle spindle or shaft. Throttle position is sensed by a contact-type switch or a potentiometer. The switch type has two contacts, idle and full load. It can be supplied with a voltage to the center terminal of its connector. At idling speeds, the full load contacts are open. The idle contacts are closed, and the signal to the computer provides for a mixture to maintain idle quality and stability. Slightly rotating the throttle shaft opens the idle contacts. As the throttle approaches the wide open position, the full load contacts close. The ECU reads the full load signal and enriches the mixture to suit. The idle contacts close signal can also be used with the engine RPM signal to the control unit to stop fuel delivery on engine overrun. This can be done, for example, if engine speed is above 2,500 RPM on deceleration. If the ECU reads a figure above this and also receives a throttle closed signal, it opens the injector electrical circuit and stops fuel delivery. As RPM falls below, say, 2,100 RPM, the circuit is restored. Injection then recommences to maintain drivability. A potentiometer type sensor monitors throttle position over its full range. One end has a 5-volt reference voltage from the control unit. The other is connected to control unit earth. A third wire runs from a sliding contact in the throttle position sensor to the input circuits of the control unit. The sensor then works like a variable resistor. As the angle of the throttle valve changes, so does the voltage signal along the third wire. At closed throttle, the reading is usually below 1.25 volts. As the throttle valve opens, the voltage signal rises. At wide open throttle, it's about 4.5 volts. This ongoing monitoring of throttle position provides more data for the control unit. This allows control over a wider range of operating conditions. This section examines the exhaust gas oxygen sensor. The oxygen sensor, also called a lambda sensor, is mounted in the exhaust manifold or the engine pipe. Its sensing portion is exposed to the stream of exhaust gas. It detects leftover oxygen in the exhaust gas and sends the data to the control unit. The control unit uses it to fine-tune the pulse it sends to the fuel injectors. The sensor consists of a tube closed at one end and made of zirconia ceramic or titanium ceramic. Its inner and outer surfaces are coated with platinum. The outer closed end is covered by a louvered metal shroud that protects it from breakage but still lets the exhaust gas contact the tube. Its inner surface is in contact with the air. A wire contacts the inner surface of the tube through a spring and an electrode bush. This provides the electrical link to the control unit. The inner and outer surfaces of the ceramic tube are coated with porous platinum. The side facing the exhaust gas has a highly porous ceramic layer on top of the platinum, which lets oxygen through. The ceramic tube with its platinum electrodes is now a porous solid electrolyte. At temperatures around 350 degrees, it becomes a conductor. One side detects the level of oxygen in the exhaust gas. The other detects its level in ordinary air. If the levels are different, a voltage is generated between the two sides. The control unit compares this voltage to a preset level. Below the level indicates a lean mixture. Above it means a rich mixture. The control unit may then adjust the pulse to the injectors to maintain correct mixture. This fine-tuning is needed for the catalytic converter to function properly. Some sensors have a built-in heating element powered by the vehicle's electrical system. This section examines auxiliary air valves. They are part of the cold start system. The auxiliary air device has a connecting hose from the intake air side of the throttle plate to its controlling passageway. A return hose then connects from the passageway to the plenum chamber. The controlling passageway is covered or uncovered by a blocking plate or disc, which is acted on by a bimetallic strip. The strip is heated electrically by a heater coil. The heating current is turned on when the engine starts. The heating effect bends the strip, which turns the blocking plate. As it turns, it changes the cross-section of the controlling passageway to control the additional air required. In a cold engine, the passageway is at its maximum set opening. Then, as the engine warms up, it gradually closes. This section examines idle speed control devices. The solenoid-type air control valve acts on signals from the control unit to bypass a measured airflow around the throttle plate. The position of the valve depends on how much current the control unit applies to the solenoid. Maximum current flow opens the valve fully to give maximum airflow. This is generally the assumed position for starting. Thereafter, the taper valve is positioned by pulsing the solenoid winding circuit at a predetermined frequency. The amount of valve opening, and therefore the amount of airflow, depends on the on time of the pulse. A long on pulse with a short off pulse will produce a high average voltage, and therefore a large opening of the valve. A short on pulse with a long off pulse will produce a low average voltage and a small valve opening. This on and off time is called the duty cycle, and it's generally expressed as a percentage. Variations in pulse width at the set frequency is called pulse width modulation. The stepper motor type of idle control positions its tapered pintle using a screw and nut assembly. The nut is part of a centrally located permanent magnet armature. It engages with the screw on the pintle. Rotating the armature extends or retracts the pintle, which closes or opens the air passage. Rotation occurs by switching current flow in two coils. The pintle turns in forward or reverse steps, numbered from 0 with the bypass air passage fully closed, up to 255 for maximum airflow. Such a large number of steps allows the pintle position to be finely controlled. When the idle speed is controlled by the position of the throttle plate, a DC motor may be used as a variable throttle stop. The controlling circuit can let current flow through the motor in either direction to extend or retract the linear actuator. Solenoid valves can also be used to bypass a predetermined amount of air around the throttle plate. These may come into operation for specific load compensation. For instance, when the air conditioning compressor is engaged. They open up a passageway of fixed dimension and do not vary the opening. This section examines injectors. In engines with multi-point injection, the injectors inject fuel into individual intake tubes, directly in front of the engine intake valves. The injection valve, or nozzle valve, is held against the valve seat by a helical compression spring. A movable plunger is rigidly attached to the nozzle and supported in a guide in the lower section of the injector body. The plunger is acted on by a solenoid winding, wound onto the injector body. Each end connects to a terminal. The control unit completes the injector electrical circuit. It provides pulses of a set duration, so that the injector valve opens and closes or pulses very quickly. Electrical pulses pass through the injector winding and set up a magnetic field that draws the plunger and valve away from the nozzle seat. Fuel held under pressure in the fuel rail can now pass through the filter and the center of the injector and enter the inlet port. In a single-hole injector, fuel is injected in a finely atomized conical spray at an angle of about 25 degrees. The exact injector open time depends on the data the sensors give the ECU, but it usually varies from 1 to 20 milliseconds. Valve lift for the fully open position is about 0.15 millimeters and response time is about 1 millisecond. Rubber moldings or O-rings seal the injector in the manifold and at the fuel rail. This helps prevent the transfer of heat to the injector and the formation of fuel vapor bubbles under heat-soaked conditions. Director plate injectors operate on the same solenoid principle. 4 minute holes for fuel delivery direct jets of fuel toward each other, so that they collide and break up into a cone-shaped spray. In some engines with 2 intake valves, the injectors have 4 holes, but only 2 jets directed towards each valve. This ensures good fuel distribution for efficient combustion and emission control. The jets are set very precisely, and they must be located accurately by means of the fuel rail. In side-feed injectors, the injector is located integrally with the fuel rail and fuel flows through the side of the injector near the bottom of the injector body. Fuel vapor is easily carried away by the return fuel, which provides easier starting when the engine is hot. Resin-molded connectors are used to reduce noise and to retain and locate the injectors in the fuel rail. All injectors are calibrated so that in any application, the nozzle valve lift and the annular gap between the nozzle valve and the injector body is the same for each injector. Fuel pressure is held constant, so the only quantity that can change is how long the nozzle valve is held open, and this is what determines how much fuel is delivered. This is called the pulse width of the injector and is decided by the control unit. The injectors fitted must have the correct calibration. Color coding of the terminal adapter can be used for identification. The injector used for throttle body injection is similar to that used for multipoint. It has a nozzle and spring-loaded plunger operated by a solenoid. When the injector opens, fuel is sprayed into the intake air, passing through the throttle body. There may be 1 or 2 injectors which open and close at a frequency set by the control unit. At low engine RPM, this frequency is low. As engine speed rises, so does frequency, until at some point the valve may not close completely, and then it may deliver an almost continuous spray of fuel into the intake air entering the manifold. In some cases, a cold start injector is fitted. It's a solenoid-operated valve on the intake manifold or plenum chamber. It is in the main airstream on the engine side of the throttle butterfly, and it's supplied with fuel under pressure from the fuel rail. A turbulence nozzle injects the atomized fuel into the airstream during engine cranking. The operation is controlled by the action of a thermotime switch. This section examines the thermotime switch. The thermotime switch controls the operation of the cold start injector. It's fitted to the cylinder head casting with its lower portion immersed in engine coolant. This lower portion houses a bimetallic strip that reacts to coolant temperature. A heater coil is wrapped around the strip. Heating and cooling of the bimetallic strip opens and closes a set of contacts. This interrupts and completes the circuit for the cold start injector. When coolant temperature is below the rated value of the switch, the contacts are closed, and so is the circuit for the cold start injector. Then, during cranking, the cold start injector will spray fuel into the manifold. If coolant temperature exceeds the rated value of the switch, the bimetallic strip bends and opens the contacts. That means that when the engine is above a certain temperature, the cold start injector won't operate, and this prevents excessive wetting of the spark plugs and a rich mixture on startup. The heater coil also limits the operation time of the cold start injector up to a maximum value depending upon the application. Typically, this can be about 10 to 12 seconds at a temperature of -20 degrees Celsius. The heater coil is energized during cranking, and if the engine fails to start within the specified time, the bimetallic strip bends under heating action and opens the circuit. This prevents flooding the engine with excessive fuel. The time limit is automatically reduced for temperatures up to the rated value of the switch. At that value, the contacts open under the influence of the coolant temperature. This section examines crankshaft position sensors. There are different kinds of crankshaft position sensors. Inductive type sensors sense the movement of the ring gear teeth on the flywheel or a toothed disc on the crank pulley. These sensors do not make physical contact. The sensor is mounted on the crankcase wall. It consists of a stator with a central permanent magnet and a soft iron core surrounded by an induction winding. The housing around all of these components is insulated from them. The stator is positioned so that it has a very small clearance or air gap between the end of the soft iron core and the flywheel teeth. As the flywheel rotates, the teeth approach and leave the stator and the air gap changes. As this occurs, the strength of the magnetic field changes. The winding is part of a complete circuit, so changing the magnetic field produces an alternating voltage and current. As the tooth approaches the stator, the strength of the magnetic field is increasing. This induces a voltage and current flow in the winding. The polarity of the voltage is said to be positive, as it produces a current flow in the winding in a certain direction. When the tooth aligns with the stator, the magnetic field is at its strongest, but at that point it is not changing. Voltage and current flow fall to zero. As the tooth moves away from the stator, the strength of the magnetic field changes again, and once again voltage and current flow is induced in the winding. This time, current flow is in the opposite direction, and the polarity of the voltage is now said to be negative. Since polarity changes every time a tooth approaches and leaves the stator, the voltage produced is an AC voltage, and the current flow in the winding is an alternating current. Similarly with the tooth disc. As the tooth approaches the stator, the magnetic field is changing. It reaches a maximum when the tooth aligns with the stator, then changes again, decreasing as the tooth moves away. An alternating voltage is produced. It is the frequency of this alternating voltage that is used by the control unit to calculate engine RPM. Hall effect sensors operate by using the potential difference or voltage created when a current-carrying conductor is exposed to a magnetic field. If a magnetic field is applied at right angles to the direction of current flow in a conductor, the lines of magnetic force permeate the conductor and the electrons flowing in the conductor are deflected to one side. This deflection creates a potential difference across the conductor. The stronger the magnetic field, the higher the voltage. This is called the Hall effect voltage, and if the magnetic field is alternately shielded and exposed, it can be used as a switching or signaling device. Hall devices are made of semiconductor material because it produces a better effect. The Hall generator and the integrated circuit, or IC, are located on one pole of a permanent magnet. Battery voltage is supplied to the positive connecting lead and current flows through the semiconductor material. With the magnetic field exposed, lines of magnetic force permeate the conductor. The Hall voltage is at a maximum and the Hall IC is active. As soon as one of the screens enters the air gap, the magnetic field is shielded and the Hall voltage falls to a minimum. This continual establishment and interruption of the magnetic field causes the Hall voltage to be turned on and off, and it is used as a switch or a signaling device. The optical type sensor uses the release of light energy from a light-emitting diode called an LED, and the detecting of this light by a photodiode. The diodes are aligned with each other, and a signal rotor passes between them. The LED also has connecting terminals and a plastic lens to diffuse the light. Slits in the rotor plate interrupt the light being sent from the LED to the photodiode. This on-off signal is used to detect engine RPM and to detect crank angle position.